They told us the future of intelligence. It was built on a mountain of hardware. They said that more power was the only way forward. But here's what they didn't tell you. They didn't tell you about the wall, the memory wall. And they for sure didn't tell you it was built to keep people like you out. They call it the KV cache. Think of it as the model's short-term memory. Every single word you type, every token it processes, you're just feeding the beast, and it grows and grows. It's a linear, completely unforgiving equation that just eats your VRAM alive. You know that 8 billion parameter model you've got? Well, a 32,000 token context is going to cost you over 4.5 gigs of VRAM, and that's for the cache alone. You see, the problem wasn't the size of the data. It was the shape. It was full of these outliers, rogue data points, these massive activations that were 100 times bigger than everything else around them, just distorting the entire space. And they break every single attempt at simple compression. So the question had to change. What if you didn't try to crush the data? What if you just turned it?
Google's answer was called TurboQuant, and it's basically 2 steps. First, you rotate the vector. It's a random turn deep in high-dimensional space that just spreads the energy out, tames those outliers. It makes the data uniform. Then comes step 2, a little 1-bit trick, an error checker called QJL that uses a single bit of information to make the math honest. It's a shift in geometry, not a reduction in information.
And the numbers. Well, the numbers were nothing short of a revolution. 6 times less memory, just 3.5 bits per value. And the big one, 0. Accuracy loss.
Look, don't take my word for it. Just look at the data. Find that Turbo 3 row. Perplexity, that's how we measure a model's quality. Lower is better. It's at 5.460. That's virtually identical to the 8-bit baseline. Now what about speed? 1.02x. It's just as fast. But the compression? 4.6 times better. The data doesn't lie. The wall, it finally had a crack in it.
So Google published the math. And here's the crazy part. They didn't even release the code. But they didn't have to. The community, they took the paper and in a matter of days turned pure theory into a weapon. Llama CPP, MLX, PyTorch. Suddenly it was running on Apple Silicon, on NVIDIA. The revolution wasn't televised, it was compiled.
And this is what it all means, right here. That 12-gigabyte card sitting on your desk? Yesterday, it hit a hard wall at 16,000 tokens. It was done. Today? Today, it's processing over 100,000. That's an order of magnitude increase, overnight. The entire game, it just changed. For everyone.
But let's be clear, make no mistake, this is not a silver bullet. It only compresses the cache, not the model weights themselves. And the biggest models, the 70 billion parameter monsters, the paper didn't even test them. And yeah, on smaller models, anything under 3 billion, you can actually see the quality start to suffer. And then there's the fight. A serious dispute brewing in academia about who really got there first. The truth, as always, is complicated.
For years, the race was all about scale. More parameters, more hardware, more raw power. But that's the old race. This breakthrough, it signals the real start of the new one. And this new race, it's all about efficiency. It's about clever math. It's a future that's not defined by brute force, but by elegant, smart compression.
TurboQuant didn't tear the wall down. It just showed everyone how to build a door right through it. So no, the wall isn't gone. It just moved. Which leaves us with the real question. What's the next breakthrough? And who is going to be the one to find it?